Hi there! Now we will have a deep dive into data drift detection techniques. We will cover quite a lot of very interesting things, like data drift detection methods and strategies for choosing optimal drift detection approach for your particular problem statement and dataset. We are going to cover special cases like detecting drift for large datasets, detecting drift for real-time models, and using drift as the retraining trigger. And finally, we are going to touch questions like how to interpret prediction and data drift altogether and what to do after data drift is detected. So, let's start from data drift detection methods. When we just start thinking about data drift detection, the first option which comes to our mind is using statistical tests. And this is fair enough, because statistical tests generally help us to test the hypothesis whether two data samples have equal distribution or whether one data sample has a known distribution with specific values of parameters like specific standard deviation and specific mean, right? And of course, this idea is very well applicable for data drift detection. And the good news is that even if you have only one dataset, like current batch of data, and for some reason you have no access to your reference dataset, you can still use statistical tests to detect drift. For example, in this case, you can use one sample that test or t-test for mean, or one proportion that test for proportion, right? But be careful here, because in this case, you need to generate some hypothesis on the values for distributions, and it's good when you have very interpretable features like, for example, salary or age or something else, and you can come up with the assumptions like, I believe my feature have normal distribution with mean equal to 50, and in this case it's good idea to use such parametric tests. But if you cannot really come up with such expectations, that's quite hard, right? In this case, it's always better to generate somehow your reference dataset, and as soon as you got your reference data, you can use two samples parametric tests to compare distributions. And it's much easier, because here you just need to compare your reference data with the current data, and you can use tests like, for example, to sample z-test or t-tests for means, but of course for normally distributed features. And that's actually quite important note. If we discuss parametric tests generally, we can say that they are quite demanding into the particular parameters for your data samples. Like, a lot of tests assume, for example, that your data are normally distributed. This is why they have quite limited space to be used for, right? Good news is that parametric tests are very sensitive, especially compared to non-parametric tests, and if you work on very sensitive problem statement, for example, something related to healthcare, then it makes sense to use parametric tests. However, it's quite hard to fine-tune and select the right test for each individual feature, especially if, well, you have quite a lot of such features and they have different types and different distributions. In this case, you might need to invest quite a lot of time into selecting the right test for each feature. But for small datasets and sensitive problem statements, it definitely makes sense. The other approach we can use is non-parametric statistical tests. The good news is that they are less demanding into the properties of your data samples, and this is why more widely used. The idea here is to check whether the samples have equal distributions, and for doing that you can use Kolmogorov-Smirnov test, K-sample-Anderson test, Pearson chi-square test, and some exact tests like Fisher and Bernard's. Of course, each statistical test have its limitations and reasons to use. For example, some tests is better to use for categorical features like Pearson chi-squared. Some tests can be used for numerical features and categorical features as well. But be careful here and make sure that you selected the right statistical tests. If you compare non-parametric tests to parametric tests, they are less sensitive in terms of drift detection, but they are more widely applicable in terms of data sample characteristics. Some of them can be used for B-model distributions, and that's very good news. Luckily, we can use the distance-based approach for drift detection, because if you move from the statistical tests to the general idea of drift detection, our problem is to check whether our data has changed quite a lot, and it doesn't necessarily mean that we need to use statistical tests for that. Basically, we just need to have any metric or function which helps us to compare two distributions. And this is why distance-based approach works quite well here. We can use approaches like Wasserstein distance or Jensen-Shannon divergence or PSI, which is population stability index. And the good idea is, the good thing is that if we use something from these distances, it will be much easier to interpret the results. Because when it comes to statistical tests, what we generally have as an output is p-value, which is quite hard to interpret, especially for non-technical specialists. But when it comes to distance, it's much easier to understand how far two distributions are from each other, and this is good news. Together with distance-based approach, we can also use domain classification models to detect drift. And here is a very interesting idea. So the idea is to use binary classification model to distinguish between two data samples. And it can be applicable for different data types, like tabular data, some unstructured data like text or images or even encodings, or some multimodal data sets. So that's quite good news. Actually, the idea is to train a binary model which will try to distinguish between the reference and current data. And if your model is good enough and the quality of the classification is high, it means that model is quite confident into telling which data row comes from the reference or the current data. And this means that there are some certain differences, which is basically a data drift, right? So that's a very nice approach to detect data drift as well. And here I want to make an important note that data drift detection is a heuristic. It's not like a mathematical law, right? This is why it's quite important to make sure that you understand why you actually analyze your data for data drift and what method makes sense for you. Whether you want to have very sensitive methods, and in this case it makes sense to use parametric tests, or you want to have a pretty interpretable approach to data drift detection, and in this case it makes sense to use distance-based approach, or maybe you have quite a lot of data with different types like text, images, encodings, and tabular data, and you just need to have an integral estimation of whether the data are different, and in this case domain classification is quite good choice. We have a very interesting blog which related to the topic of selecting the right data drift detection method, and if you're interested, I suggest you to take a look. Here's a link for you. And we are moving to the next question. How to choose the data drift detection approach for your particular problem statement and dataset. So basically, I'm going to introduce to you two options. And first option is go with defaults. Here you will need to start from a few assumptions, like whether you want to detect drift for the whole dataset, or maybe you have few very important features and you want to detect drift for those features individually, and then pick a metric and threshold and really pick something default, like for example Wasserstein distance and the threshold equal to 0.1, right? And then it's a good idea to just start use it, like start drift detection or drift monitoring, and at first time do some visual evaluations, like see the results, see the distributions, and decide whether you are happy with the results or not. And this work can be automated as well, because you can, for example, check whether you often have some false alarms, or maybe you miss some moments when you wanted to get an alarm but you didn't get it, and by doing that you can actually adapt and use maybe different, more sensitive or less sensitive drift detection techniques, or maybe tweak your threshold. So this is the first option. Start from the defaults, at first visually analyze the results, and finally adjust the methods to be the best for you. Here is the second option, which is called experiment, and it works only if you have some historical data. So the idea here is to tweak the parameters of your drift detection approach based on your historical data. If you have quite a lot of data, then definitely there were some stable periods where there were no data drift, and maybe some periods where you had data drift. If not, you can definitely create it synthetically, like change a couple of values for some data rows, and by doing that, introduce the synthetic drift to your historical data. And then you can select some drift detection methods, maybe again start from the default, apply it to your historical data, and see whether you had quite a lot of false alarms and whether you were able to detect all the moments where you had synthetic or real data drift. And by doing that, you can come up with the best option for you, so to see whether your drift detection method was able to detect all the important moments on top of your historical data and didn't generate to you quite a lot of false alerts. As soon as you're done with tuning, you can just reuse this approach to your monitoring, and this is quite good. So this is why it's always important and good to have quite a lot of historical data. It helps with a lot of tuning, not only for model retraining, but also for setting up the right monitoring. Well, at this point, we discussed different drift detection techniques and strategies to choose the optimal drift detection technique for your dataset and problem statement. Now let's discuss some special cases which might be useful for the monitoring. And first is handling quite large datasets. Because, well, it's quite often when we start to use some statistical tests for drift detection, and then we find ourselves with applying the statistical tests for the large datasets. Unfortunately, that's quite a bad idea because statistical tests was made for work with samples, and if you are not willing to create the samples, then a lot of statistical tests will be oversensitive for your data and will always send you a lot of false alarms, right? It's not what we want to end up with, and in case you have quite a lot of data, it makes sense to either pick a sample. If you have like tons of data, you can just go for the random sampling. If not that's a lot of data, you can go for some stratification and make sure that your sample has, for example, the same proportions of data from different class if you work with classification problem statement, or maybe you want to do stratification by other features, but make sure that your sample is representative, right? So in this case, if you created a sample, you can use any statistical test or other drift detection techniques which works for like smaller data. Or if you still don't willing to create a sample, you can go for bucketing. This is also a very interesting idea because the basis of this idea is to aggregate your observation in order to decrease the amount of data. For example, if you previously tried to detect drift on top of the individual events, you can, for example, aggregate those events into sessions and detect drift on top of sessions, for example. Or maybe if you used like a minute data to detect a drift, you can aggregate it to hours and detect drift on top of hourly data. So that's the idea of the bucketing. In this case, you do not need to like select data, so it's not like a sampling. So if you are not sure about the right sampling techniques, maybe the bucketing is the good option for you. The next case is non-batch models, and that's quite interesting because when it comes to data drift detection, generally we always like have in mind that you have some reference data and the current data and we compare to those distributions, right? But in case we have like continuous model, we just do not have any fixed data sets, right? And we need to come up with the idea of how we will create this reference and current data in order to have some batches and apply drift detection techniques for those data samples. And the idea here is to use some window function. For example, you can select the weekly window or hourly window, or maybe do it each minute or each 10 seconds. And in this case, you just need to make sure that you use the right window function approach. Those can be the size of your window or step size, decision whether your window should be intersecting or not, whether you need to move your reference dataset as well or not. So it's all the question of experiments, and if you have historical data, well, you know what to do, right? And if you already picked the window function, you can, by doing that, use the different windows as the batches of data and then apply drift detection methods, distance-based, domain classifier, statistical tests to compare those window data and detect the drift. So it works very well for continuous models as well. So even if you have the real-time model, you still are able to detect drift. Finally, I want to touch a topic of drift detection and using drift detection as the retraining trigger. There are some pros and cons of this idea, so let me a little bit elaborate on this. Personally, I would not recommend you to blindly retrain your model every time you detect drift, and here are some reasons. First of all, data might be low quality, and if you detected the drift, The reason of you have a drift might be that there is some problem with data processing or maybe data quality at the data source, right? And in this case, if you will retrain your model on this new corrupted batch of data, the model will be useless, right? So this is why it's quite important to understand what is the source of your data drift. Also, data might be insufficient for new model training because you do not have enough data to retrain your heavy model. Data may be even not representative. For example, there is some unstable period like pandemic or some seasonal spike, or maybe there is some events happening and this influences your model. So in this case, it also doesn't really make sense to retrain your model on this non-representative batch of data. Instead, consider understanding data drift and using data drift as the investigation trigger. So if you detected a drift, for example, for quite a lot of features, it makes sense to take a look at your data and see and figure out what is the reason for drift. So maybe it's better to have a drift as the investigation trigger or labeling trigger, and then based on your analysis decide whether you want to actually retrain your model or maybe do something else, like fall back to some rule-based system, or maybe just do some experiments with different types of models, so maybe you can come up with the better solution for your task. Well, finally, let's talk about the interpretation. So how to interpret data and prediction drift together? Well, there are quite a lot of nuances, and this is again the reason why I do not personally recommend you to blindly use data drift as the trigger for retraining, because sometimes the drift doesn't mean that you have any issues with your model at all. Let's assume data drift is detected, and here I mean features drift, but prediction drift is not detected. It can be a quite positive scenario where none of your important features drifted. In this case, your model is robust enough to survive drift and you actually do not need to do anything. But it can be also a negative scenario where your important features changed, but model should have reacted somehow on this, but it didn't. So in this case, you need to intervene into something. Vice versa, let's assume that data drift is detected and prediction drift detected as well. In this case, it can be a pretty positive scenario where, for example, all important features changed, but model reacts and extrapolates really well. For example, your prices go lower and model predicts the higher sales, so that's actually good news. You trained really good model, no need to intervene. It can be a negative scenario where important features changed, but model behavior is unreasonable. Right, so model behavior also changed, but not the way it expected to be changed. And in this case, we need to intervene. Well, what to do after drift is detected? And it's a very important question. Luckily, we have a blog about it, so if you're interested to explore it in a lot of details, I would suggest you to go to this blog, but now I'm going to briefly discuss it with you. So first of all, if your drift is detected, you need to check data quality, and I personally believe that's the best first step. Why so? We need to make sure that our drift is real, so it caused by some changes from the environment, but not the issues or problems with the data processing steps. So let's check that there is no problems with the data sources. Maybe there are some problems with the data processing or missing queries or whatever. So if there are any issues with data quality, we need to check it first, then recalculate data drift, and only after this do something with model if it's needed to be done. For example, it can be a case where, for example, part of our data was lost due to error in the login, and in this case we can see that there are quite huge differences into the distributions, for example, from regions. And the problem actually was that for some regions we had problems with the login. In this case, we really don't need to retrain our model, right? We need to go back to the login system, solve the issues, and, well, continue use our existing model. Next step, if there are no data quality issues, would be to understand drift. So in this case, I would say that you see that there are quite a lot of changes in your data, and it's good to have some visual exploration, like visually explore distributions, maybe analyze changed correlations, check some descriptive statistics like means, maybe min-max ranges, medians, etc., and evaluate different segments. Is there a real-world interpretation? Maybe it's new marketing campaign launch, so it's good to check it and discuss it with the domain experts so that you know what is the reason for drift and know how to react respectively. For example, it can be some significant change in the correlation between some statistics, for example, page views and your target function. In this case, it's good to go to the domain experts and discuss what can happen. Maybe there is a very nice interpretation and explanations, and it will help you to come up with a good idea of how to fix that. Third, funny thought is that doing nothing is also an option. For example, maybe if you see data drift but cannot understand what has happened, you need to send some new data to the labeling process and wait until you got these new labels to see what's going on. Maybe it was the false positive alert because, a lot of, for example, statistical tests have a certain, all statistical tests actually have a certain level of the false positive reactions, right? And you might get it, actually. In this case, you do not need to do anything because it's false positive. You might want to just continue to monitor for a drift because it can be just very volatile drift detection methods, and if you continue to monitor, your drift can be just stabilized and there is no data drift at all. Or maybe the drift is real, but you trained so good model which adapts really well, and in this case you do not need to do anything at all. So finally, quite often we need to actively react on drift. In this case, you can explore quite a lot of options depending on what we have implemented for our machine learning service. So if there is some fallback systems, like for example another model or some rule-based system, we might to switch to the fallback system. Either we can retrain our model if we have enough data, right, for retraining, and there is no corrupted data which we detected drift on top of. We might need even rebuild or update model totally if there is quite a lot of changes and maybe our algorithm we used before to train the model is no longer optimal. Or maybe we need to tune some model or apply some post-processing rules, like change our threshold for fraud detection, for example, from 50% to 80% or vice versa, right, depending on the case. And we just discussed quite a lot of things. We discussed what are different drift detection methods, how to choose the best drift detection approach for your dataset and problem statements. We also discussed some special cases like handling large dataset, calculating drift for real-time models, and using drift as the retraining trigger, right? And how to react, what to do after drift is detected. So now I believe we have enough information to go to the practical part and see how we can evaluate drift in Python. Let's do it.